Students, one more problem. This isn't in your notes. I'll just describe it here and then we'll solve it. I'm going to set off a firework. Firework has a little motor, a little rocket motor, and the engine puts out 560 joules of work. Now, the details of that, we can go and ask Mr. Brown about that. That's taking a chemical potential energy, the gunpowder in the rocket engine or the nitrate and fuel or however you make it. You know, you take the fuel and you burn it and you turn that chemical energy, in this case, into the kinetic energy the uh, of the rocket going up, and also that you'll have some energy lost in the exhaust. Next chapter we can talk about that. What happens when the exhaust comes out and the rocket goes up? But for the moment, we'll say that the engine does work on the rocket body of 560 joules. So when the engine quits, we'd like to know what the velocity is. And then we'd also like to know how high it gets, because after the engine quits, this rocket's going to continue upwards in free fall. So this is a fairly straightforward problem. What we're going to do is say that external work equals the change in energy. Now there's another way we could go about it. We can say that the total work done equals the change in kinetic energy. So you could do that, but you would also have to factor in gravity here, that there would also be a gravitational work. So we don't want to completely go about this path. This is long compared to this. We'll just do the change in energy is the external work. Well, the change in energy is going to be based on the final energy when the rocket engine quits and the initial energy when it starts. Oh, we'll also put out that the engine quits at, say, 50 meters, let's say. I hope this works. If it doesn't work, you will never see it. So the change in energy here is E final minus E initial. Well, what's E initial? Well, you start this thing on the ground, V is 0, and H is 0. So E initial is 0. E final is going to be 1/2 mv squared plus mgh. Oh, we need some mass here. Let's say it's 1 kilogram. So what we'll have here is our external work is going to be the amount that we use. So 560 joules. And now we just have 1/2 1 kilogram v squared plus 1 kilogram times 10 meters per second squared times 50 meters. So this stuff over here is 500 joules. And we'll have 1/2 times 1 kilogram times v squared. So we'll rearrange this v squared. The difference in these is 60 joules over 1 kilogram. And that is going to be v squared is 120 meters squared per second squared. So 120 square root is v is 10.9 meters per 10.95 meters per second. So we could, using this number, go and get the maximum height through kinematics. But I'm going to propose that we don't do that. Up here, by definition, the velocity is zero. So we can do the same work here to get the maximum height. We can say that external work from the engine is 560 joules. And then what we have, well, E initial is still zero. E final is 1/2 mv squared plus mg h max. This term is zero, so 560 joules is 1 kilogram times 10 meters per second squared times h max. And now we can solve, and what we get is that h max is 56 meters. What this looks like more than anything else, I would say, is bookkeeping. When we are doing energy, we are accounting for the energy somewhere, right? Is that at every stage in a problem, there's some energy. The rocket on the ground has chemical potential energy. When the engine quits, it has a little bit, well, actually a fair bit of potential energy and some kinetic energy. And when it gets up to the top, it has only potential energy. But at every step, we can account for the total energy. And what we're doing here is the chemical potential energy. We don't actually know how to deal with it, so we treat it as external work. And we just care about the rocket or the object that's moving and the Earth. And so we'll do problems like this more and more as y'all work through it this week, is dealing with the work that's done on an object and how it changes the kinetic energy and how it changes the potential energy. So, to summarize all of that stuff, we had, right, this is a summary. We had that the work is the force vector dotted with a displacement vector. And for the purpose of this, I'm just going to use the F delta x cosine theta definition. So there's our definition. The work for a single force. So the net force gives you the net work. So the net work is sigma F dotted with delta x. And this is just adding up all the forces. And so you'd have a bunch of force vectors and you do the vector addition of them. But this has to be the change in kinetic energy, where the kinetic energy is 1/2 mv squared. So if we do the work for gravity, it is going to be minus mg delta y, and that leads us to define the potential energy U is mgh, and the work that gravity does is minus the change in potential energy. And we can take this work and kinetic energy theorem and relate the change in kinetic energy looks like minus the change in potential energy if there's no external work. This is just for gravity. All right. But it leads us to something more general, is to say that the mechanical energy is 1/2 mv squared plus mgh, and this is conserved, right? E final equals E initial if no external work. But when there is external work, it is just E final minus E initial. So that summarizes everything. Is we start with work as a definition here, and we go through and we define the kinetic energy. So define kinetic energy, define potential energy, define the mechanical energy, and either energy is conserved or you can identify an external force that does external work. All right. So finally, there's one more thing we can ask, because we've never mentioned time in any of this. We can ask the rate at which work is done. So the power, P, is defined as work over time. That's all it is. So, but we can talk about the work, but sometimes it's a little bit easier to go ahead and say that the work is F dot delta X over delta T. Just to go ahead and use the definition of work. And so we can also define the power as, if you look in here, there's a velocity in here. But it is the average velocity. So you can define problems where what we care about, we can work with the velocity and the force and get to power. So sometimes you want to know the power. I think I give you something in the notes. First, define the power and talk about some units. The example we have is climbing a set of stairs. All right, so let's find that problem here. We climb up the stairs of this 90-story building. So in 5 minutes, we make delta y is 300 meters. And so we can ask how much, what was the rate that power is used. We can also ask the energy that we need to expend. So we're taking the potential energy in the chemicals in our food and we're converting it, which is not exactly an efficient process. We're converting it into, in this case, potential energy. So 5 minutes is 300 seconds. Delta Y is 300 meters. We're going to say our mass is 50 kilograms. So the energy used, which is really the potential energy, is mgh. 50 kilograms times 10 meters per second squared times 300 meters. And we'll do the math here. 500 times 300 is 150,000 joules. So you note in the previous slide, I gave you some other definitions. The calorie that we use in chemistry is 4.186 of these joules, and it's based on heating water up. The food calorie that we use is based on 4,186 joules. So if we divide by 4,186, we find it used 36 calories to climb up that high. Exercise doesn't burn calories at nearly the rate you would like to burn them. What it does is it keeps you fit. It keeps you functional. It also helps. It makes you strong so you can do stuff. You know, the point of exercise is to stay fit, not to burn calories. Just so you're aware of that. The thing that helps you if you're trying to stay fit is eating the correct number of calories and of the correct forms, which you can talk to Miss Phillips about. Not me, obviously, because I'm not good at any of that. But climbing a 90-story building, which changes your elevation by 300 meters, is 36 calories. Anyway, we've got this number here. We want to know the power. So the power is energy over time, or work over time, or force times velocity. But in this case, it's 150,000 joules over 300 seconds is 500 joules per second. There's a unit for this. 1 joule per second is 1 watt. So this is 500 watts. So if you can climb a 90-story building in 5 minutes, you are using energy at the rate of somewhere between 5 and 8 or 9 incandescent bulbs that are 60 or 100 watts, which is quite a lot. So we could ask some other questions here, but in general, actually, let's ask another question. We can come up with one question. Let's say you are driving down the road. So here's your car, and you're driving down the road at 25 meters per second. We can ask, based on the combined friction and air resistance, we'll say that there's a resistive force, which is, let's say it's 600 newtons. Your car is probably 500 kilograms, so it's probably 5,000 newtons, let's say. That's a good ballpark, 5,000 and 10,000 newtons. And so we'll ask, what is the power you need to maintain this speed? So if we want to know the power that's used here, we could do some other stuff, like say, well, in 1 second, this will be 25 meters. And so we could do 600 newtons times 25 meters is 15,000 joules. Or we could just note that the power is going to be the force times the velocity. And so our force here is 600 newtons times 25 meters per second is 15,000 watts. 15 kilowatts is a lot. Just for your information, we can turn this into horsepower. We'll divide by approximately 750, and this is 20 horsepower. So I think these numbers deliberately. This is about 60 miles an hour, and this is not at all realistic. But this is why your car has, a engine that has, dozens of horsepower, up to hundreds of horsepower, is the resistive forces of air resistance and friction in the tires limit. They set, at some point they set a speed that you can reach. Basically, there's only a certain speed that you can maintain because your losses will eventually end up just, you'll slow down as much as you can speed up. Right? So that's why cars have a top speed. Anyway, this is fairly straightforward, I think. The next video I'm going to do is going to be completely supplemental. It's not going to have anything to do with the work you're doing. But we talked about air resistance here. We talked about forces. We ought to do at least one thing where we talk about air resistance as something to study. So